Welcome to the Second International Conference on Computing Innovation and Applied Physics. My name is Emanuel Indrei, and the title of my talk is on the first eigenvalue of Laplacian for polygons. The principal frequency of a domain is the frequency of the greatest proper tone of a uniform and uniformly stretched elastic membrane in equilibrium and fixed along the boundary. In 1877, Lord Rayleigh observed that of all membranes with a given area, the circle generates the minimum principal frequency. This discovery was in the context of numerical evidence and a computation of the principal frequency of almost circular membranes. This property was mathematically known as the Rayleigh conjecture. It was proven by Faber and Cron at the beginning of the 20th century. If one considers the unit ball, the principal frequency is the first positive root of the Bessel function. However, the principal frequency of a triangle is generally inaccessible via an explicit formula. In 1947, Pauli proved that of all triangular membranes, with a given area, the equilateral triangle generates the lowest principal frequency. In this context, he also proved that the square generates the minimal principal frequency among quadrilaterals with a given area. And he used Steiner symmetrization in his proof, where the set is transformed into a set of the same area with at least a line of symmetry. Nevertheless, if one considers polygons with sides greater or equal to 5, the technique in general increases the number of sides. Pauli mentions in the article that it is natural to suspect that the propositions just proved about the equilateral triangle and square can be extended to regular polygons with more than 4 sides. In their 1951 book, Isoperimetric Inequalities in Mathematical Physics, Pauli and Zego talk about the principal frequency problem in a less confident way. To prove or disprove the analogous theorems for regular polygons with more than 4 sides is a challenging task, and afterwards the problem was known as the Pauli-Zego conjecture. And Rowe includes this in his book Extreme Problems for Eigenvalues of Elliptic Operators, and he mentions that a beautiful and hard challenge is to solve the open problem too. In my approach to address this problem, I combined isoperimetric tools with tensor theory tools. The isoperimetric tools involve the following. Suppose that one considers a polygon in terms of a subset of R2, and in the sense that it's generated in terms of n vertices. Then one can consider the center of mass of these vertices to be the origin, and consider corresponding radii in terms of connecting the center of mass with each vertex. Then one can consider fixing one vertex and then looking at the segment that's generated in terms of the center of mass in this vertex, and then going clockwise in a consecutive manner and looking at the next vertex, and then constructing the corresponding barycentric angles of the polygon. To investigate the Pauli-Zego conjecture, one can consider then a large class of polygons in the sense of vectors in R2n comprised of x and r, x being a vector in Rn, r being a vector in Rn, and xi and ri are greater or equal to 0, and then one has that the barycentric angles sum to 2 pi, that's encoded in this first property. The second is that the area is assumed to be alpha, which is just a fixed constant. And then the origin is the center, which is encoded in the 2 equations in 3. The geometric feature of this set is that it's a 2n minus 4 dimensional manifold. And each point can be thought of as a polygon centered at the origin with barycentric angles x, area alpha, and radii r. One can think then of the regular n-gon with vertices on a unit circle in terms of the vector generated by 2 pi over n and 1. To connect this with the isoperimetric inequality, one can consider the isoperimetric deficit in terms of polygons in these coordinates, and then one can consider the corresponding variances of the interior angles and the radii. To think of this in a precise manner, one can think of an inequality relating the isoperimetric deficit with the corresponding variances. And that's something that I proved in a paper that was published in 2016 and also was built on earlier work from a paper that was published in 2015. To firstly outline my result, I'd like to first state the theorem that I proved in 2022 in terms of this Pauli-Azeglio conjecture, and it states that there exists a computable number greater or equal to 5, so that for all n greater or equal to this number, there exists an explicit set alpha n, which is a subset of this 2n minus 4-dimensional manifold, so that Pn, the convex regular n-gon, has the smallest principal frequency among all n-gons in this set alpha n. To understand the tensor theory tools, one can think of the variational formulation of the eigenvalue problem in terms of a function that then is a minimizer in terms of this ratio. And this function has a special property. It's then an eigenfunction in terms of the Laplace operator, and it characterizes the shape of a membrane when it vibrates, emitting its deepest tone. Supposing that ST is an evolving surface and A is an object defined on this evolving surface, the invariant derivative has the following definition. And one can also think of the invariant derivative analytically. Suppose that you have surface coordinates and then a parametric equation for the surface, and the velocity object is the t derivative, and then the surface projection is this dot product. And then one can consider this equation in terms of the invariant derivative. Now, one can also consider the surface's speed, and one can also consider what the corresponding formulas would be in terms of this tensor calculus via having a surface restriction of a special field, so that one has this chain rule, and then one therefore also has a corresponding product rule in terms of the invariant derivative. Supposing that omega t evolves and its boundary is given by st, then there are also formulas for computing the derivative with respect to t of the corresponding integrals in terms of omega t and the surface st. And note that in the equation for the derivative with respect to st, one has that the curvature tensor appears in the sense that the trace of the curvature tensor is the mean curvature, which appears in this integral here. In the classical perturbation theory, the bulk equation is a standard Laplace eigenvalue equation. And in quantum mechanics, the sign convention is that the operator is positive definite. Also, this bulk equation is coupled with the Dirichlet boundary condition that U is 0 on the surface. And for convenience, U is normalized in L2. To analyze then the perturbed system, the bulk is differentiated in the normal sense. The boundary condition is differentiated in this invariant derivative sense. And then the normalization is then differentiated in the normal t derivative sense. And therefore, one has three equations. One can take the first equation, multiply through by u, and then integrate over the set omega t, and then employ the last two equations to compute the derivative of the eigenvalue. Then, since the surface gradient vanishes because of Dirichlet boundary data, one has a formula for computing this dot product in terms of the normal, since the normal will be parallel to the gradient. And then one can consider differentiating this to obtain the second derivative, which is given in terms of this formula. To quickly go through the proof, one can consider a polygon P whose area is fixed to be, let's say, pi, and then consider three consecutive clockwise vertices, V1, V2, V3. they generate this triangle. Then one can consider this triangle and then symmetrize with respect to the Steiner symmetrization relative to the line that's orthogonal to the line generated by V1 and V3. And therefore V2 then evolves to V2 star, and then one can keep track of this evolution in terms of parameter t. With this, one can then consider the corresponding parametrization in terms of the data, and one sees then that in terms of the polygon, in the complement of this triangle, everything stays fixed. The only thing that changes is this triangle. And one then has the evolution to an isosceles triangle. Now, one can consider PT to be the evolution in terms of the Steiner symmetrization, and then one can look at the standard Laplace eigenvalue equation in PT. And then one can consider the Dirichlet boundary condition and then the normalization. And the differential equations then are in terms of this top equation, and then one also has that on the boundary there is this corresponding equation. Now, if one stays away from the vertices, let's say WT is a point in R2 which stays away from these vertices and is on this line L12, then in the neighborhood of WT, there is enough regularity of U to extend U slightly in that neighborhood. And because of the Dirichlet boundary condition, N is parallel to the gradient. And therefore, this simplifies to an equation like this. But because one can extend U, one can extend this equation in the neighborhood. And therefore, one can differentiate this equation. And by differentiating this equation, one obtains this formula. With this, then one can simplify the second derivative in the sense that one can replace this relatively complicated term in terms of the cancellation that happens with this term and this term. And one then ends up with a formula for the second derivative which is simplified. Hence, because one can convert the parametrizations into the tensor theory context, one can then calculate the first derivative in terms of everything that was given, and then use Taylor's theorem to obtain this expansion. And after doing this, one can iterate this in a clockwise consecutive way, and therefore this generates a sequence of polygons, and then one can define a polygonal space in terms of looking at polygons whose vertices are in neighborhoods of the vertices of the convex regular polygon, so that when one considers this flow, it converges to the convex regular n-gon, and there is a certain specific additional technical rate associated with this convergence. However, when one considers triangles, then this rate can be proven. Hence, it's very natural. Now, the isoperimetric deficit in terms of the standard literature is encoded in this formula. And supposing that the first symmetrized polygon is not the polygon that one initially starts with, then the isoperimetric deficit is strictly decreased. Now, one can iterate this and then obtain this series in terms of the iteration, and therefore one can compare the limit with the initial in terms of this series. When n is large, one can consider the eigenfunctions of the unit ball. And these are in terms of Bessel functions, and therefore one has additional information when n is large in the context of Bessel functions. With this and complicated W2P theory and BMO theory, one can obtain a gradient bound. In a sort of addition to this, one can also obtain the corresponding information from the isoperimetric stability in terms of the discrepancy of the collection of polygons from the convex regular polygon in terms of the T, which was encoding the symmetrization difference. With this and several technical inequalities, one can obtain a bound on the two series, and hence one can prove that the eigenvalue of the polygon that one initially started with will be then greater or equal to the eigenvalue of the limit plus the sum of these two series, but the sum of these two series will be greater or equal to 0, hence the eigenvalue of the initial polygon will be greater or equal to the eigenvalue of the limit, which is the eigenvalue of the regular convex n-gon. To understand what happens with low values of n, one can consider something along these lines as a starting polygon, and this is in terms of heptagons, and in about 27 iterations, that converges to the convex regular heptagon. One interesting feature is that what one started with is not that close to the convex regular heptagon. Nevertheless, there is this very efficient convergence. If one considers something along these lines, this converges in about 55 iterations to something like this. This is equilateral, however, it's not cyclical. This is then the feature that comes up for low values of n, and one can think of it in terms of cyclicity. For large values of n, cyclicity is naturally imposed in terms of Pn being close to the ball. One can also think about a reduction in terms of understanding that for large values of n, Pn is close to the ball, and therefore there is an underlying feature where one can utilize elements from the stability of the regular Fabre-Cron inequality to construct a large space of polygons where one can show that the convex regular n-gon is the minimal element in that. And it's in terms of this corollary. And combining that then with the previous one, then has a large space of polygons where the Polyakov-Szego conjecture is then true. To see how this works, suppose one has polygons EK and the area is pi, and one then just supposes that the limb sup of this infima is greater than 0. One then has that the limb sup of the eigenvalues is greater than the eigenvalue of the unit ball. And to prove this, suppose that this is false. Then instead of this strictly greater than, one would have less than or equal to then. But the Fabre-Cron theorem indicates that it will be an equality, and then the limb sup is the lim inf, which is the limit, and therefore one has that the limit of the eigenvalues of these k-gons then is the eigenvalue of the unit ball. And then if one considers a sequence that achieves the limb sup, let's call it this EKL, then up to translations, it's contained in a large ball because of the following. Suppose that it's not true, then one has that one side approaches in terms of the length plus infinity, but the area is fixed, and therefore the EKL will be a subset of RKL, where RKL is a rectangle with one side which approaches 0. So one has basically this very thin rectangle that contains the corresponding polygon. And then, because for rectangles one can explicitly compute the eigenvalues, one then has the information that the eigenvalue of the rectangle approach is plus infinity, but one has this bound from the variational characterization, and therefore that's a contradiction. And with this, one conveniently assumes convexity, but one can remove the convexity assumption to generate a larger class. And then, because all the EKL, therefore, are in a large ball, there is a convergent subsequence, and the limit has area pi. And then, via Chenet's theorem, one has that the eigenvalues of the EKL converge to the eigenvalue of E. Now, with Faber-Cron, one has the information that the eigenvalue of this limit is strictly greater than the eigenvalue of the unit ball, because the lim sup of this infima is strictly greater than 0. Therefore, EK cannot be close to translations of balls. With this, however, then one contradicts the fact that the limit of the eigenvalues of the EK is equal to the eigenvalue of the unit ball. Now, when one considers all of this, it shows the following. So, the limit of the eigenvalues of EK is equal to the limit of the unit ball, implies that the limit as k approaches infinity of this infima is equal to 0. And therefore, that generates a continuity statement in terms of modulus of continuity between these two. And it's in terms of there exists a modulus of continuity, so that assuming that the area of the polygon is pi, one then has that the eigenvalue difference with the eigenvalue of the unit ball is greater or equal to this modulus the infimum of translations in terms of the Lebesgue measure of the symmetric difference of the polygon with B1 plus X, where X is the translation. So this is in terms of taking the infimum over all translations and then finding the essential optimal translations, which generates this minimization. Therefore, up to this translation, the largest possible value that the Lebesgue measure of the symmetric difference between the polygon and translation of ball can be is in terms of the eigenvalue difference. Suppose that one can then think of it in terms of taking EK to be the eigenvalue difference. This is strictly greater than 0 by the Faber-Cron inequality. And then one can construct the polygonal space in terms of polygons, so in this case k-gons, so that the modulus applied to the Lebesgue measure of the symmetric difference is greater or equal to EK, where the translation is the one that is the best fit in terms of satisfying this infimum. And then subtracting and adding the eigenvalue of the ball, one can therefore prove the following inequality in terms of the difference of the eigenvalue of the n-gon and the eigenvalue of the convex regular n-gon, in the sense that this is greater or equal to this modulus applied to this Lebesgue measure of the symmetric difference minus this En. And this is then greater or equal to 0. And therefore, lambda Pn is less than or equal to lambda of E for any E in this set. And this already shows the minimality of the convex regular n-gon in this polygonal space. Now, one can combine this with the earlier space that I talked about, and then have a global space where the Polyak-Szego conjecture is then true. Now, in 1951, Polyak and Szego also discussed the problem of finding an explicit formula for the eigenvalue of a triangle. With this, I actually obtained a formula with the following contextual information. The principal frequency of a triangle with given area A is given in terms of this formula, where one looks at the sequence of polygons, in this case, sequence of triangles, that's in terms of this partial flow that I alluded to earlier. And then one has the derivatives show up in this formula. And therefore, this is one formula for the principal frequency. One different sort of context would be to understand this in terms of just one iteration, where one takes an arbitrary triangle, and then after one symmetrization, one ends up with an isosceles triangle, and then one can compare the eigenvalues, and that's encoded in this statement, where T iso is given in terms of the symmetrized triangle. Note that here one can use the initial data in terms of the triangle T is ABC, and then it has given area rho, and then the sides are given in terms of this order without loss of generality. And then one can write this formula in terms of this data, and then also the eigenfunction. Now, in terms of constructing the space of polygons, the equivalence of the scaling invariant principal frequency deficit and the scaling invariant polygonal isometric deficit appears. And this addresses a 2006 conjecture of Antunes and Freitas. And it's in terms of this result, there are these two inequalities that relate to deficits. The way that the conjecture was stated was in a sort of more complicated way in terms of these two inequalities. And then, in addition, because they performed some numerical experiments, they also conjectured the value of this coefficient. I constructed for each epsilon between 0 and 1 a triangle so that it has area 1, and these two inequalities are true. Note that if epsilon is close to 0, then the middle is squeezed between values which are very close to pi squared over 16. And therefore, one has that this coefficient is less than or equal to pi squared over 16. This is actually less than the conjectured value, which is approximately 0.67, which was in terms of the numerical experiments. Now, the equivalence also solved the sharp polygonal fiber-Cron stability problem for triangles with the explicit constant. One can consider this in terms of the Frankel symmetry and then prove that this inequality is true. And here, 2 is the sharp exponent. And one can also construct a simple example of a pair of non-isometric simply connected domains in the Euclidean plane, which are isospectral. This was due to Gordon, Webb, and Volpaire. And there's also another construction which was discovered by Milner, which exhibits two 16-dimensional toruses, which are distinct as Riemannian manifolds, but have the same sequence of eigenvalues. However, one can hear the shape of an equilateral triangle due to polia, and my stability theorem yields that one can compare frequencies and detect a near equilateral triangle. With this, one only requires one eigenvalue, not all of them. Also, there is this interesting application in terms of electron bubbles. Electron bubbles form when electrons enter into liquid helium. The electrons repel the helium atoms and form these areas free of helium, which are known as cavities. The equilibrium is obtained in terms of minimizing this energy, where one has the surface tension density, the hydrostatic pressure, the eigenvalue, and then Planck's constant, and the electron's mass. With my technique of generating this large collection of polygons, for which the Polya-Zergo conjecture is true, this actually also exposes the bubble equilibrium, which can be computed by a scaling argument and polygonal isometric inequality. The statement is that if one considers this energy, then in this space of polygons, one has that this energy is minimized by this dilation of the convex regular n-gon, where the dilation satisfies this fourth order equation via these physics constants. Last year, Bogoshel and Bukur showed that the local minimality of the convex regular polygon can be reduced to a single certified numerical computation. And for n equal to 5, 6, 7, 8, they performed this computation and certified the numerical approximation by finite elements, modulo machine errors. And this is in terms of the local minimality, not the global minimality. That's all I wanted to say. Thank you for your attention.